Assalamualaikum. Today my group will be presenting related rate. We will present definition, application, problem and solution. First of all, an introduction. Related rates problem involve two or more variables that change at the same time, possibly at different rates. If we know how the variables are related and how fast one of them is changing, then we can figure out how fast the other one is changing. This usually involves writing an equation relating the two variables and taking the derivative of the equation with respect to time. Implicit differentiation is often used. Applications of related rate. Examples. Example 1, situation 1, a ladder falling. Situation 2 or example 2, an inflating balloon. Problem statement. We found 3 problems to solve. The first problem is a spherical balloon is being filled with air at a constant rate of 2 cm³ per second. How fast is the radius increasing when the radius is 3 cm? Second problem. A ladder is leaning against a wall and the base of the ladder is being pulled away at a constant rate of 2 meters per second. The ladder is 5 meters long and is initially 3 meters away from the wall. At what rate is the top of the ladder sliding down the wall when the base is 4 meters away from the wall? The third problem. A water tank in the shape of a cone is being filled with water at a constant rate of 4 m³ per hour. The height of the tank is 8 meters and the radius of the circular top is 6 meters. At what rate is the water level rising when the water is 4 meters deep? My name is Muhammad Adam, student ID number 2022801798. I will be solving problem 1, which is inflating balloon. A spherical balloon is being filled with air at a constant rate of 2 cm³ per second. How fast is the radius increasing when the radius is 3 cm? Step 1. First of all, we have to identify the volume of a sphere of radius, which the formula for that is V equals 4/3 pi r³ cm³. Step 2. Since the balloon is being filled with air, both the volume and the radius are functions of time. Therefore, t seconds after beginning to fill the balloon with air, the volume of air in the balloon is volume of time equals 4/3 pi r time cube cm³. Step 3. Differentiating both sides of this equation with respect to time and applying the chain rule, we see that the rate of change in the volume is related to the rate of change in the radius by the equation V of time equals 4 pi r time square r time. Step 4. The balloon is being filled with air at the constant rate of 2 cm³ per second. So, volume equals 2 cm³ per second. Therefore, 2 cm³ per second equals 4 pi radius times square centimeter square times r times centimeter second, which implies r times equals 1/2 pi radius times square centimeter per second. The answer is when the radius r equal 3 cm, radius times equal 1/18 pi centimeter per second.
Hi, I'm Muhammad Farid Shami, 202228264778. Moving on to our next slide is problem 2, which is a ladder falling. So, given that the dx over dt is 2 meters per second, which is the rate at which the base of the ladder is moving away from the wall, and the x is given as 4 meters, which is the distance between the base and the wall, and y is the unknown height. Step 1. To solve the problem, we need to find dy over dt, the rate at which the top of the ladder is sliding down the wall when the base is 4 meters away. We can establish a relationship between x, y, and the length of the ladder, which is 5 meters, using the Pythagorean theorem. X power of 2 plus y power of 2 equals to 5 power of 2. Step 2. Differentiating both sides of the equation with respect to times t. 2x times dx over dt plus 2y times dy over dt equal to 0. Substituting the known values, we substitute the known values, which is 2 times 4 and times 2 plus 2y times dy over dt equal to 0. Simplifying, 8 plus 2y times dy over dt equals to 0. Solving for dy over dt, 2y times dy over dt equals to negative 8 and dy over dt equals to negative 4 over y. Step 3, we still need to determine the value of y when the base is 4 meters away from the wall. Using the Pythagoras theorem, 4 power of 2 plus y power of 2 equals to 5 power of 2. 16 plus y over 2 equals to 25. And next, y power of 2 equals to 9, which resulting in y equals to 3. Step 4, now we can substitute the value of y into dy over dt equals negative 4 over y. dy over dt equals to negative 4 over 3. Therefore, when the base is 4 meters away from the wall, the top of the ladder is sliding down the wall at the rate of negative 4 over 3 meters per second. Note that the negative signs meaning the ladder is falling down.
Hi, Assalamualaikum. I'm Muhammad Nazirul bin Ramli, student ID 2022603232. I'm gonna share about problem T. It is water tank. Given dV over dt equal to 4 meter cubic per hour, rate at which the tank is being filled with water, H equal to 4 meter. It is depth of the water. Alright, let's move to the solution. Step 1. To solve the problem, we need to find dH over dt, the rate at which the water level is rising when the water is 4 meters deep. We can establish a relationship between the height and the radius of the water surface using similar triangles. R over H equal to 6 over 8. R equal to 6 per 8 H. Alright, step 2. To find the volume of the water in the cone, we use the formula for the volume of a cone. V equal to 1 over 3 pi R square H. Substituting the value of R in terms of H, V equal to 1 over 3 pi 6 over 8 H square H. V equal to 1 over 3 pi 9 over 4 H cube. Alright, let's move to the step 3. Differentiate both sides of the equation with respect to time. dV over dt equal to 1 over 3 pi multiplied by 9 per 4 multiple 3h square dH over dt. Substituting the known values, 4 equal to 1 over 3 pi multiple 9 over 4 multiple 3 4 square dH over dt equal to 4 equal to 1 over 3 pi multiplied by 9 over 4 multiple 48 dH over dt. Alright, let's move to this step 4. Simplifying. 4 equal to 12 pi multiple 3 dH over dt. 4 equal to 108 pi dH over dt. dH over dt. dH over dt equal to 4 per 108 pi. Therefore, when the water is 4 meters deep, the water level is rising at a rate of 4 over 108 pi meters per hour. Alright, for the conclusion. In conclusion, related rates revolve all around the world, showing how significant this topic is to meter.